So have you ever been reading a science fiction novel or maybe watching one of your favorite sci-fi shows or movies and a character says something and you're not sure, is that technobabble or is that real science?
It just occurred to me that I could set up a frequency harmonic between the deflector and the shield grid using the warp field generator as a power flow anti-attenuator, and that, of course, naturally created an amplification of the inherent energy output.
Sometimes it's pretty obvious, but sometimes it can be hard to tell, especially if you're not a scientist yourself. Hi, I'm Dr. Matthew Huddleston, physics professor and science fiction author. And I'm going to use this series of videos to talk about some ideas that are commonly used in science fiction stories and help you understand the real science behind them. So we're going to start today by talking about the Lagrange points.
Now that we're more in range, what can you tell us about the target? Coordinates are in the Lagrange point of the two black holes, which means that the progenitor's tech has been in gravitational equilibrium.
So are Lagrange points a real thing? Well, it turns out they are. Actually, they're special orbits that are extremely important for a lot of the space science that's done today. And to understand why, we have to remind ourselves how basic orbits work. Now, an orbit is just a balance of sorts between an object's own inertia that tends to make it want to go at a constant speed in a straight line. That's Newton's first law of motion. And the force of gravity towards some central object. Let's say a satellite is orbiting the Earth. The satellite would go at a constant speed in a straight line away from the Earth, but gravity wants to make it fall towards the Earth, and the combination of those two results in a circular path around the Earth. When you do the math, you find that for a circular orbit, you need to have a very specific speed that depends on how far away you are from the central object. And it doesn't matter if it's satellites orbiting the Earth or moons orbiting planets, planets orbiting stars. The orbital velocity depends on how far away you are from the central object. For example, Mercury, being the closest planet to the Sun, takes about 88 days to orbit the Sun, and it moves at a whopping 106,000 miles per hour. But Jupiter, which is much further away, it takes about 12 years to orbit the Sun, and it moves at about a third of the speed that Mercury does in its orbit. So where the Lagrange points come in is when you have three objects instead of just two, when you're solving for what's called the three-body problem. So if we want to know how an object will interact with not just one other object, but two others, so you have something that's feeling the gravity from the Sun and the Earth, say. Now we have three objects, and when we're trying to figure out orbits, it becomes a little more complicated. Now, normally, if it was just something orbiting the Sun and you wanted it to orbit at the same rate that the Earth orbits the Sun, it'd have to be at exactly the same distance away from the Sun. But when you're solving for the three-body problem, actually it turns out that there's another location called the first Lagrange point, or L1, that's a million miles closer to the Sun than the Earth is. And yet objects placed there will actually orbit at exactly the same rate that the Earth does. They'll take exactly 1 year to orbit, and they'll stay in line with the Earth as the Earth orbits the Sun. Now, likewise, there's another position called the second Lagrange point, or L2, that's about a million miles further away from the Sun than the Earth is, and objects there also will orbit at the same rate that the Earth does. The reason this happens is this is a special kind of balance where the gravitational pull from the Sun on an object here at L1 would normally require much faster speed for its orbit, but because the Earth is pulling from the opposite direction, things balance out so it goes at the same rate around the Sun. And likewise, at L2, normally objects here feel less of a pull of gravity from the Sun, so they'd lag behind the Earth, but since the Earth is pulling on it too, they catch up and they move at the same rate. So that special balance, in physics we sometimes call a balance of forces equilibrium. Now, there are two types of equilibrium. There's what we call stable equilibrium, kind of like this coin laying flat on the table, where if I move it away from its equilibrium position and then let go, it'll fall right back. But then there's unstable equilibrium, and unstable equilibrium is like trying to balance a coin on its edge. Technically possible, but just the slightest nudge away from equilibrium and it falls. Now, it turns out that the first and second Lagrange points are places of unstable equilibrium. So when we put satellites there, they tend to drift away. But we can use a little trick. We know that a little bit of rotation will make a coin easier to balance on its edge. And likewise, satellites can do little mini orbits around the L1 and L2 points that keep them more stable. Back in the 1700s in Berlin, there were two brilliant scientists, Leonard Euler and Joseph Louis Lagrange, who were working on this three-body problem. And independently, they came up with solutions that were these L1 and L2 positions. But Lagrange came up with three more, the L3, L4, and L5 positions that I didn't talk about. And so he got the Lagrange points named after him. Now, we have about a dozen satellites at the L2 Lagrange point currently. The most famous would be the James Webb Space Telescope, you may have heard of. It's making measurements of very faint objects in the distant universe, stars and galaxies at great distances. And to do that, it really needs to not have radiation from the sun interfering with it. So it sits in the shadow of the Earth. Constantly, as the Earth orbits the sun, it stays in the Earth's shadow at that L2 position, and that helps greatly in its ability to make those faint measurements of distant stars and galaxies. Likewise, we've got about a dozen satellites at the L1 position, and most of them are monitoring particles and fields on the way from the sun to the Earth, and that helps us do predictions of space weather, which I'll talk about in another video. And a much more sinister example of how a Lagrange point can be used is highlighted in my new novel, Final Eclipse, coming out this fall. It's a fast-paced, hyper-realistic sci-fi story where young adult characters struggle to survive as the Earth is plunged into disaster. It will be available for purchase in the fall of 2024 at most all the places where you find your favorite books. Check the QR code or the link below to see regular updates and new videos that explain other science concepts from the book. This is Dr. Matthew Huddleston. Whether creating or calculating, always remember to do your research.